Hey guys, this is 6.3, 6.4, part 2. We're looking at graphing logarithmic functions. Alright, so on the left here, you see we have the graph of the parent function log base b of x, where b is greater than 1. b is greater than 1. And on the right, we have the same thing, but on this one, we have b is between 0 and 1, so b is a fraction between 0 and 1. So notice that when b is greater than 1, the function is increasing on the entire interval, and then when b is between 0 and 1, it's going to be decreasing. Okay, and notice some key things about these graphs. You've got a vertical asymptote instead of a horizontal asymptote like you did on the exponential function, and it is at x equals 0. You have an x-intercept at 1, 0 there. And think about it, that's because if you plug in 1 for x, you have log base b of 1. And remember, log is saying b to what power equals 1. b to what power equals 1. And so that's always going to give you 0. Anytime you have a 0 in your log, you're going to get, anytime you have a 1 in your log, you're going to get 0. All right, and then our other point that we have is b1. So that's log base b, and we're plugging in b for x. Well, b to what power equals b? And that would just be 1. So those 2 points are always going to be on your graph unless you've been, unless some type of transformation has happened. So no matter what b is, you'll have those 2 points. Now, log is the inverse of exponential, so to show you this, I've put it in my calculator. I've got y equals 10 to the x, and then log base 10 of x, so the same bases. And then if I look at the graph, you can see that they are reflections over the line y equals x. In fact, I can graph that line, y equals x. Okay, and you see that each point is just a reflection. Each point on the blue line is a reflection of a point that's on the red line. And so that is, a definition of an inverse function. You're going to be, the graphs are going to be reflections over the line y equals x. On your exponential function, you had the y-intercept, excuse me, you had the y-intercept at 0, 1, so switching the x and the y, right? And you had a key point at 1b, so switching the x and the y. And so that's another thing that shows you that these are inverse functions, is that those points were on the exponential graph, but the x's and the y's switched places. All right, so domain of these functions. It doesn't matter whether b is greater than 1 or if b is a fraction. The domain is going to be from 0 to infinity, not including the 0, because you have that vertical asymptote, which means it's never going to cross or touch x equals 0. The range for both of them is all real numbers. You're going down forever here. You're going up forever there. Same thing over here, up and down. So you're going to hit all possible y values. Your asymptote for both is at x equals 0, that vertical line. X-intercept is at 1, 0. And you do not have a y-intercept because of that asymptote. Your other key point that you have on this graph is b1. b1, whatever b is. All right, so those are the graphs of the parent functions, and then, that changes depending on what b is, but those key features that we just talked about will not change. So let's try graphing some of these. All right, so given a logarithmic function with the form f of x equals log base b of x, like we just talked about, first you want to draw and label the vertical asymptote, x equals 0. So first get that asymptote, x equals 0 on the graph. Then you can plot your x-intercept, which is always going to be at 1, 0, that key point at b1. And then once you have those 2 points, you can draw your curve through those points. If you follow those steps, everything should work out to where your function is decreasing if b is between 0 and 1, and increasing if b is greater than 1. But that's just something you can check to make sure you actually drew the curve correctly. All right, so on A, I'm going to first draw my vertical asymptote at x equals 0 to remind me that I can't cross or touch that one and I need to approach it. Plot the x-intercept at 1, 0. So there's 1, 0. And then the key point at B1. Well, our B in this case is 1/3, so that point is going to be 1/3, 0. So 1/3, somewhere between, somewhere closer to 0 than 1, and the y value is 1. So another point right there. All right, now I can draw my curve through those 2 points, approach that asymptote, and there you go. Also notice that because our b was a fraction, it is decreasing. So just checking to make sure it's decreasing, and it is. All right, on b, we're gonna draw the vertical asymptote here. Vertical asymptote, x-intercept at 1. Key point at B1, so our B is 5, so that's going to be 5, 1. So 1, 2, 3, 4, 5. Y value is 1. And then we can draw our curve through those points. This one's a lot flatter. Could just be how I drew it, but... All right, there it is. All right, and there are some things that can change the graph of your log function, of course. So let's look at transformations of log functions. I've already talked about transformations this year, this semester actually. And it turns out those exact same transformations apply to the log function, right? So this number in front, A, is going to cause a reflection if it's negative. So negative causes a reflection over the x-axis. If it is between 0 and 1, so a fraction, it's going to be a vertical compression. And then if A is greater than 1, there'll be a vertical stretch. Okay, so A will do all of those things. And then your C here on the inside, it's going to shift your graph left and right. So if you have x minus a number, it's going to move to the right. If you have x plus a number, it's going to move to the left. And then our D here is going to go up and down. So if you have plus D, it's going to go up. Minus D is going to make it shift down. All right, so let's use those transformations to graph these functions. Oh, I just realized I forgot to talk about the domain and range up here. That's okay. Your domain going from 0 to infinity, and your range goes from negative infinity to positive infinity, just like it did when we talked about the graph on the previous page. And same thing here. 0, make sure you put a parentheses there because we're not actually hitting 0. And then negative infinity to infinity. All right. So first of all, we know that there are some key points that are, quote, always on the graph of a log function. And so that's going to be our x-intercept at 1, 0, and our key point at B1. Well, this one, let's talk about what transformation we have here. This plus 2 is going to make it go left 2, right? So each x value is going to have 2 subtracted from it. The y value is not going to change. I don't want to write that right there. Hold on. So xy is your original point, and we know we have 1, 0, and b1. But now we're moving left 2, so it's going to be at x minus 2, and your y does not change. Okay, so I'm going to just transform those 2 points. So subtracting 2 is going to give me negative 1, 0. My b in this problem is 3. So normally 3, 1 would be there, but we're moving left 2, so it's going to be at 1, 1. All right, and then also think about your vertical asymptote. Your vertical asymptote is normally at x equals 0, but now it's shifted to the left 2, so it's going to be at negative 2. All right, so using those 3 things, we can easily sketch this graph. So think about where your vertical asymptote would be. Well, if I move left 2, it's going to be at negative 2. And then think about where your x-intercept should be. It's at negative 1, 0. And then think about where that key point's going to move to, 1, 1. All right, and now we can sketch the curve. And there you go. All right, let's look at D and kind of do the same thing. So what transformation happened here? This is going to make it move up 2. So now our xy is going to go to x comma y plus 2. Adding 2 to your y values. So the point 1, 0 is going to become 1, 2, just adding 2 to that y value. Your key point is going to be 4, 1, but now it moved up 2, so it's going to be at 4, 3. And what about your vertical asymptote? Does shifting up 2 change where that vertical asymptote would be? If I take this vertical line and I move it up 2, is that going to change anything? No, it's still going to be at x equals 0. All right, so let's plot our points. We've got 1, 2. We've got 4, 3. So I've got a point here. Okay, and there's the graph of that log, roughly sketched. Let's try one more like that. All right, on E, we've got a negative in front, so remember, what does that mean? That means we've got a reflection. That's going to make it reflect over x, which means that each y value is going to take on a negative. So x, y is going to become x comma negative y. But then what does this minus 3 do? That makes it move to the right 3. So that takes your x value and adds 3 to it. So I'm going to have x plus 3 here. And that's how each point will get transformed. Well, we're just going to use our easy points, our 1, 0, our x-intercept, which is going to become 4, 0. Can't make a 0 negative. And then you've got your key point at 2, 1. Just using the base there to get that 2. So that's going to become 5, negative 1. Okay, think about these transformations. Do they affect your vertical asymptote? Well, your vertical asymptote's normally at x equals 0, but this got reflected over x. Does that change your vertical asymptote? No. Reflecting that vertical line will not change it, but shifting it to the right 3 will. So you're going to add 3 to that, and that will make it at x equals 3. Basically, whatever transformation happens here to the x, whether it's shifted left or right, is going to affect where your vertical asymptote is. Just adding 3 to that, so it's going to be at 3. And then we can sketch our points at 4, 0. Our x-intercept is at 4. And our key point is now at 5, negative 1. Okay, going through both of those points, I'm going to have to approach my vertical asymptote as I go up. And now it's decreasing. So notice that because it reflected over the x, that function is now decreasing instead of increasing. And you can always check these in your calculator, right? If you go to y equals and just type it in. So let's see what this one would look like. Unless your calculator will not let you change the base of your log, which is okay. It just won't be an exact graph. If you use log base 10, it won't be exact, but you can kind of see like what the general shape should look like still. So you can do log. In my calculator, I can do log base, hit math, go up. You see log base. I can change that base to a 2. X minus 3. And there's the graph. That blue line should keep going up. It's just the calculator stops it because it is such a vertical line that it almost identifies it not as a function, right? So it just stops, but it should keep going. All right. Last thing I want to mention in this video is the domain of a log function. So we've looked at a lot of graphs, and actually we should have been doing the domain of all of these. So what's the domain of this function? Well, it can't go past that vertical asymptote. So it's starting at 3, and then it goes to the right forever. On our previous ones that we just did, right here, our domain starts at 0 and goes to infinity because of the vertical asymptote. It's always where the vertical asymptote is. This one starts at negative 2 and goes to infinity. And the range for all of them is all real numbers. But if you're just looking at the function, there is a way to identify the domain. So this is something that you're going to add on to your restrictions on the domain of a function. So remember our other 2 restrictions that we have, and that is that anything in the denominator cannot equal 0. So I have 1 over x, x cannot equal 0 because we can't divide by 0. The other restriction on domain we've talked about this year is if you have an even root, like a square root, then whatever is inside of that root has to be greater than or equal to 0 because we can't take the square root of a negative unless we want to involve imaginary numbers. So denominators can't equal 0. What's inside the radical has to be greater than or equal to 0. And now we're adding on one more thing when it comes to logs, and that is that the argument inside the log has to be greater than 0. You can't take the log of a negative number. Let me show you. Log negative 3. Error. Okay. If I try log of negative 0.5, surely it's not even that much of a negative number. Error. No, won't work. And then also it has to be strictly greater than 0, not equal to 0. You can't take the log of 0. So let's see that. Log 0. Another error. Okay, so you need to make sure that whatever's inside your log is a positive number, greater than 0. Okay, so you're gonna take whatever's inside your log, set it greater than 0, and solve for x. And then you can write your domain in interval notation. So let's see on A. What's inside the log is x minus 5. That has to be greater than 0, so therefore x has to be greater than 5, just adding that 5 over. You can write that in interval notation. Greater than 5 is going to be starting at 5, parentheses because it's not equal to, and going to infinity. If you put that on a graph, you would see that the vertical asymptote is at 5, and so your domain ends up being from 5 to infinity. All right, on B, take what's inside the log, 5 minus 2x, set it greater than 0, solve for x. So I'm going to subtract 5, divide by negative 2. Now don't forget, when you divide by negative, you're going to flip that inequality, make it less than, and you'll have 5 halves, positive 5 halves, or x is less than 2.5. So less than is going to be negative infinity to 2.5 or 5 halves. Parentheses again because there's no equal to. And you could check that on the graph. If I just wanted to make sure that my domain was correct there, I could go in here and say log 5 minus 2x. See what that graph looks like. Okay, and you see that it cuts off right here, right at about 2.5. So yeah, your domain is negative infinity to 2.5. All right. And that's it for your notes on logs.